Hi, welcome to Dr. Raz, the Baking Chemist. So today's question is a Year 2 A-level question. It's all about entropy, Gibbs free energy, water, melting, boiling. It's a 10-mark question. Let's get into it. So it's split over 2 pages, excuse that. The sketch graph below shows how the entropy of a sample of water varies with temperature. Okay, so the sketch that they usually give you is this. Be aware that this sketch, I'll explain it and then I'll ask you what to be aware of, or I'll tell you what to be aware of in a minute. So the sketch is given here. So there's the entropy, okay, on the y-axis, and there's temperature in kelvins on the x-axis. Okay, and there's some weird things going on here and here at T1 and T2. Guaranteed they're going to ask you a question about that. Now be aware that this kind of a sketch, they could ask you to sketch it yourself, okay, and you'll see why and how to do it in a few minutes as we answer the question. Okay, so a 1 marker, quick question. Suggest why the entropy of water is 0 at 0 Kelvin. Well, at 0 there's complete order, or at 0 this water is completely ordered. Yeah, think about it. Yeah, just read the graph off. It says at temperature 0 there's 0 entropy. In other words, there's 0 disorder. So you can say it in different ways. Yeah, so at 0 Kelvin there's 0 entropy. In other words, this system is completely ordered. Okay, but think about it. Yeah, what we're saying is that absolute 0 temperature, the particles of water, remember, they're frozen at that temperature and they're not even moving, so there's absolutely no disorder at all. Okay, anyway, a number of ways you can say it. Okay, what change of state occurs at temperature T1? All right, so at that temperature, what change of state occurs? All right, remember, this is about water. Yeah, so obviously at absolute 0, that's like -273, it'll be frozen, right? So think about what's happening. Yeah, frozen. So as you increase the temperature, still frozen, and suddenly there's a slight increase, a jump in disorder. So that means what could have happened? Visualize it. What could have happened to that frozen block of ice? Yeah, what could have happened was it could have melted. So what change of state occurs? Well, it goes from a solid to a liquid. Okay, all right, next question. Explain why the entropy change, delta S, at temperature T2 is much larger than at temperature T1. So at T2, why is this jump a lot larger than this one? Okay, now continue with your sort of visualization of the block of ice. Okay, so at this point, it's melted, right? And so now it's a liquid, and you'll continue to heat it, right? Heat it. What could happen? Common sense, right? It's turned into gas. So it's boiled off. So the water here is boiled off. So the question is, why is the entropy change at that point bigger than the entropy change at this point? And the reason is very simple. It's because there's a lot more disorder, or increase in disorder. So there's a lot more disorder compared to T1. I mean, it's 2 marks, so you've got to say there's a lot more disorder, but you've got to do the comparison as well, yeah? So it's a lot bigger compared to T1, right? And remember, the word sort of bigger or compared to you need for the second mark, okay? You can't just say that the entropy is big, yeah, or entropy increases. It's got to be comparison word, yeah, bigger than that, okay? Okay, so that's 2 marks there, so disorder. Right, next question on this part. Right, so it requires 3.49 kilojoules of heat energy to convert 3.949 kilojoules of heat energy to convert 1.53 grams of liquid water into steam at that temperature and that pressure. Okay, use this data, or these data, to calculate the enthalpy change. So that's what you're looking at, calculating enthalpy change when 1 mole of liquid water forms 1 mole of steam at that temperature. So the thing I notice is that temperature and that pressure is the same as that. Good, because that would have been a whole host of problems if it wasn't the same. Okay, so 1 mole. Okay, well, look, immediately I'm seeing, look, there's a change of units here. Here they're talking about grams, here they're talking about moles, so I might as well change that to moles, yeah, to see what happens. So 1.53 grams, well, how many moles is that? They're turning it into steam. All right, so, I mean, if you don't know this equation, where have you been for the past 2 years? This is a year 2 question, right? Number of moles equals mass over mR. So obviously, I'm changing that to moles, so it's 1.53 divided by mR of water, which is 18. And if you don't know that by heart, what can I say? But work it out, H2O. Okay, 18. And then, of course, you use your calculator, or do it in your head if you're good enough. And that means 0.085 moles. And that's moles of what? Of water, right? So what that means is that 0.085 moles, yeah, of water gives out 3.49 kilojoules. So 0.085 moles of water gives out 3.49 kilojoules of energy. Okay, so how much does 1 mole give out? Divided by 0.085, isn't it? How are you going to get 1 on this side? So divide that by 0.085, but you've got to divide that by 0.085. Because remember, whatever you do to this side, you've got to do to that side. Alright, and so that means that would be 1, and that's in the way, but never mind. And that, just work it out, 3.49 divided by 0.085, which equals 41.059. Now, at this point, I'm looking at significant figures immediately. I'm thinking, have they said how many sig fig they want the answer in? Yeah, well, they've not said that in the question, but look at the numbers they give. Yeah, 3 sig fig, 3 sig fig, 3 sig fig, yeah, 3 sig fig, 3 sig. So I'm going to give this answer to 3 sig fig as well. So that way it will be 41.1. Okay, and if you don't know about these significant figures, here's a video, all right, that you got to watch. It's right in that corner I'm going to put up, okay? You've got to watch the significant figures, the second half, yeah? It's about Freon molecules, but I talk about significant figures. And of course, the answer to this is, and because it's the entropy change, so it will be kilojoules per mole. Well, it is for 1 mole, but that's the entropy change, okay? And so that is your answer. Okay, so that's that question done. We'll on to the next one. So that's like 2, 3, 4, and well, another 2 marks probably. Okay, so that's that question. Let's look at the next question. Write an expression showing the relationship between free energy change, enthalpy change, and entropy change. Really, if you've not sat down and memorized this equation, in fact, you don't even need to sit down and memorize it. If you've been using this equation for this chapter, the thermodynamics entropy chapter, or energetics 2, if you're an Excel student, this will come to you naturally, right? So delta G equals delta H minus T delta S. Okay, that equation is key for this whole chapter. Right, for the conversion of liquid water into steam at 373 and 100 kilopascals, remember, I'm immediately thinking, okay, well, that's the same temperature as my previous question and the pressure, right? It's the same temperature and pressure. Okay, fine. For the conversion of liquid water into steam, delta G equals 0. Fine. Okay, so I know it's feasible. That's what this means, delta G equals 0. Calculate the value of delta S for the conversion of 1 mole of water. That's the same in the previous question, I'm thinking, right? Okay, fine. Into steam under these conditions. State the units. So they want to state the units, okay? So calculate the value of delta S. All right, so I need to work out delta S. They've told me what delta G is. They've asked me about the equation before, right? So look, calculate the value. So they want me to work that out. They've told me what delta G is, okay? And delta H, I worked it out in the previous question. Yeah, delta H, enthalpy change. They've asked me to work it out in my previous question. Yeah, enthalpy change, delta H. Okay, 41.1. And so I'm assuming all I need to do is do the calculations, swap the values in, rearrange it, and do the calculation. So that equation becomes 0 equals, I'm deliberately doing this sort of the long way around. There are some things you do need to show, but there are some things you don't. But I'm showing you everything, and I'll tell you which ones you need to show. Okay, so obviously I'm trying to work out delta S. So that's what I need. So I need to change this formula, rearrange this formula for delta S. Okay, so that means I need to change that. Okay, so I'm going to move this around here, delta S. Okay, so I'm going to move all of that expression to the other side, and that becomes T delta S equals delta H. Therefore, delta S equals delta H over T, and therefore, yeah, I'm just going to slot the values in. Delta H equals 41.1. By the way, here it does say if you have been unable to complete part D1, you should assume delta H is 45. Okay, if you've not been able to do that previous question, just use that. At least you'll get marks for this one. Okay, so 41.1 divided by T. Now the temperature in this equation needs to be in Kelvin, not degrees Celsius. So what I'm going to do is put that in 373 Kelvin, which equals a calculator, which equals 0.110. And what's the answer? So delta S, I'm using kilojoules here. If you don't know the units, it's kilojoules per mole. You know delta H is kilojoules per mole, and then per Kelvin. So it would be kilojoules per mole per Kelvin. Okay, so that's units. Now they did say state the units, so you've got to state the units, otherwise you lose a mark. Okay, now this, should this be 3 sig fig? 3 sig fig, 3 sig fig. Yeah, I should give it 3 sig fig. Okay, so that's the answer. There you go. Okay. Oh, and the units. Yeah, I'll put units there, but I mean, you'll get a mark there, but you could, I suppose, put units here if you like. And that is the answer. Okay, and that's your 10 marks done, right? But just to sort of highlight where students often go wrong, this is a typical sort of curve for, as I said earlier, where they can ask you to draw or sketch a curve of entropy against temperature for water, yeah, from absolute zero. And they expect you to actually expect you to draw this. What they're looking for is a slight increase. It doesn't matter if it increases more or less, but what they're looking for is this jump and this jump. This is when it melts, the water melts from ice to liquid, and this is from liquid to a gas. However, the liquid to a gas, because there's hugely more disorder, yeah, or there's a lot more disorder, they're looking for that jump to be bigger. So they could ask you to sketch it. In this question, they didn't. Some people, why the entry of water is zero at 0 kelvins, they start overthinking it. Yeah, no, it's perfect, just, perfectly ordered, or very little disorder, or absolutely ordered, or there are other words you can use as well. Yeah, but the point is that there's absolutely no disorder at this point. Okay, solid to a liquid, yeah, that's fine. If you've seen that sketch now, you'll never forget it. Probably that's melting. Okay, and that's boiling. So liquid to a gas, solid to a liquid. Explain why the entropy, yeah, I've explained that already. So I've explained that already. Now this question, yes, it's not a difficult question. Yeah, I mean, sometimes what students do is just leave the answer there. Okay, well, there you go. What they don't realize is you just worked out moles of water. That's not the answer. Calculate the entropy change. So you've got to remember this many moles, okay, gives up this much energy. So therefore 1 mole gives out what? Yeah, I mean, this is simply a matter of remembering this equation. Yeah, it's not a difficult question to remember. Okay, delta G equals delta H. Right, the only thing here, though, okay, I'm going to say you don't need this for this equation, this question. However, I'm going to tell you, you've got to be careful that in this equation, the units of delta H usually are given differently, right? When you normally have delta H, right, it's kilojoules per mole, right, isn't it? Delta S is given as joules per mole per Kelvin. Right, so the units normally are different for delta S and different for delta H. But when you use it in this equation, you've got to change these units to be consistent. So either change that to joules per mole from kilojoules per mole, or change that to kilojoules per mole per Kelvin. Yeah, so you've got to be consistent with the units, and that's where students often lose marks. And I've said it in my other entropy video as well, which I'll put up here as well. Yeah, have a look at that entropy. It's a different question. But anyway, so make sure you're aware that in this question you didn't need it. However, whenever you're trying to use enthalpy and entropy in the Gibbs free energy equation, that you do sort of have consistent units. And of course here, where students often lose marks are the rearrangement, right? So they I don't know why students have problems rearranging equations, but this is a simple equation to rearrange. Yeah, so you want to make that the subject of the formula. You move the whole lot, that's a minus there, you move the whole lot to the other side, okay, and that gives you that, okay, and then you just rearrange for delta s. This is multiplying with t here, so when it comes to the other side, you divide it. There are other ways of doing it as well, but anyway, this is one way, okay, and then you get your delta s. The only thing, the one point where they do get it wrong, and this is why the question is asked for the units, is because here delta s, because delta s is measured in, what did I say? It's measured in joules per Kelvin per mole usually. All right, so here they write down joules per Kelvin per mole, but what they don't realize is that delta H you have used as kilojoules per mole, yeah, from your previous question. This is kilojoules per mole, right? So because you used kilojoules per mole here, therefore the answer that you get would be kilojoules per mole per Kelvin for the entropy. You're not joules per mole. All right, so that's the only, and that's one of the reasons why they asked you for that particular part of the question. All right, so the marks would be 1 here, 1 here, 1 here, and of course that would be a mark. So that's 3, 4, 1 here, and then 1 for the answer, rearranging that and dividing by 0.85 to get the answer. And then you have 1 here, disorder a lot bigger than T1. So disorder a lot bigger, so increasing disorder. Yeah, disorder increases. Maybe we should put that down actually. Disorder increases. Okay, so disorder increases is a lot bigger than T1. And then that's 2 marks, and then of course that's 1 mark. That suggests why the entropy of water is 0, 0, completely ordered. That's another mark. Okay, 10 mark question. Now this one, there's a multiple choice here. 1 question. My next video will be on this 1 question. Okay, it's to do with entropy and feasibility of questions. How do you find out quickly what kind of a reaction will be feasible? That'll be the next video. Okay, just 1 question, but it won't be short. Right. Okay, well, I hope that was useful. Let me know what you think. I mean, if I were you, I'd probably try and do these calculation questions yourself without looking at my without looking at my video. Try a lot of these entropy questions. Students find these difficult, okay, and but they don't need to be, right? If you just, these are some of those questions where you just practice and you'll get them. Yeah, you'll understand them. Yeah, so keep going, and if there are any suggestions, okay, please put them in the comments below. But otherwise, if you're not subscribed yet, please subscribe, share and like, and leave a comment. Okay, I'll see you next Wednesday. Bye.